In this video, I'm going to talk about addition of angular momenta. And so I'm going to go a little bit fast through this because conceptually it's really not that difficult. Uh, but there's just a lot of calculations and a lot of tedious bookkeeping in those calculations. And so this is again just following off of the Griffiths textbook, except I've gone into a bit more detail on each of the calculations, so I've shown a few more steps, and I did some of the ones that he left as an assignment for the reader, and so that's all here. And I will link to these lecture notes in the description down below. So if you want to look at them in a little bit more detail on your own, then I would definitely recommend that. Like I said, I show pretty much every little step in each of the calculations, and so it should hopefully be fairly easy to follow along. So conceptually, when we add angular momenta, I mean, it's exactly what you think it is. So if you have a spin up, that's, an angular momentum of a half, and then you have a spin down, that's an angular momentum of minus half. You add them together, and you have a net zero angular momentum accounted for by this spin. Same if you have, a half and then another. If you have two up spins, you add them together, half plus a half, that's one. And so that's essentially the concept going on here. And so the rest of it is a lot of bookkeeping. And so, yeah, we're looking at two particles, like if you have a hydrogen atom, so you have an electron and you have the proton, which has a spin of half, which can be, either plus one half or minus one half. Or if you're looking at, two unpaired electrons, those can add up to, plus one. They can cancel each other out, or they can add up to minus one. And so we're looking at two particles in this case. And so once again, so the little one with parentheses here is just telling us so which one we're actually looking at, so which particle we're actually using this operator on. And so we use that on here, and we get our eigenvalue here. And then when we do it for the second one, we get the eigenvalue for that one. And then we do it for the z component. So this should actually be a 2 right there. So we have this, and we do the same thing. We end up with our eigenvalues. So the total angular momentum is just the angular momentum of the first particle plus the angular momentum of the second particle. And so to find the m component, or the z component rather, we just act with this on the particle system, so the two particles. So we're acting on the first one and then on the second one. We end up with m1 and the m2. We just factor that out, so it just ends up being m1 plus m2. And so I kind of put this one here big and in purple, because that, conceptually, this is kind of what it is. This one, I guess I could put this one in big purple as well. So it's just adding the total spin and adding the z components of the spin. And so, the rest of it is a lot of just bookkeeping and sort of finding out the eigenvalues and things like that. So where the total z component of two particle system M is just the sum of the two z components for each one. So for a two particle system where we have S1, so the spin 1 is equal to a half and the spin 2 is equal to a half. So you see here we have so the first two numbers here are S numbers, so it's just the spin of particle 1, the spin of particle 2. The second two is the z component of the spin of particle 1 and the z component of the spin of particle 2. So we see we have a half plus a half, so our m equals 1, half minus a half, so our m equals 0, minus a half plus a half, m equals 0, minus a half, so m equals minus 1. So this m equals 0 degeneracy is obtained when we apply the lowering operator to the spin up. So we end up with with this right here, and so we end up with this degenerate one where you can have spin up and spin down, or you can have spin down and spin up. So here I just put that this 1 over square root of 2 is just sort of a normalization factor so that the probability comes out equal to 1. So for a system with S1 equals half and S2 equals minus 1/2 for the second particle, we have just this. And so that just means that one of them can be up, the other one down, or the other one down and the other one up. So this first instance up here is what's called a triplet. These electrons are not paired. If we're considering just electrons here, they're not paired, and so their spin are independent of each other. So they could both be up, they could both be down. You could have one up, one down, or you could have one down, one up. And so that's what I show here. So for the singlet, so we could have one up and one down, or you could just switch these two back and forth and you could have one down and one up. But that's the only two options you can have. Where with the triplet, you can have both up, you can have both down, or you can have one up, one down, or one down, one up. And so that's why they call it a triplet, because there are 3 possible ways that it could happen, where the singlet is just this one. Well, it's one, but it's sort of this degenerate thing where it's a superposition of both of them. That's what this addition here means, that it's in a superposition of one of them up, one of them down, and a superposition of one of them down, one of them up. And so that is the singlets and triplets. So the spin half particles can therefore have a total spin of either 0 or 1. For the singlet and triplet state respectively. We then must show that the singlet and triplet states are eigenvectors of the S squared by finding the eigenvalues. And so this is the part where there's just a lot of sort of bookkeeping. And what I mean by that is these up and down arrows. So I've color coded them, where up arrows are all in green, down arrows are all in red. And so it's just a lot of that kind of bookkeeping. So we have this here. So this is our S squared, because we're doing S on both different particles. So we have to FOIL this out here, and we end up with this. So we have the first S squared, the second S squared, then plus 2 times the first S times the second S. And so for this, because, and we'll see here in a little bit, the S squared here are ones that we already know just from a previous video. So I want to look at just this S1 times S2. So the S1 times S2 part acting on this up down gives this. And so we have the S1x, the S2x acting. So the S1x is acting on the up, the S2x is acting on the down, the S1y on the up, the S2y on the down, the S1z on the up, the S2z on the down. And so then we just put the eigenvalues that we know from the previous video in there, and we add them up like this. And we see that this S1x flips this up to down, and this S2x flip this down to up, and same with the SYs. We're going from up to down, down to up. But then these ones stay up, and this one stays down and down. So then we just multiply these together. So the IH bar times IH bar is minus H bar, and then we have this extra minus here, so it's plus. So we end up with this right here. So this H bar times minus H bar is minus, and we have H bar squared. We factor out the H bar squared over 4, and we end up with this. These two added together end up with 2. And then we can do the same. So this is for the up and down. We can do the same for the down and up, and we end up with this same thing here. And so then if we do the S1 times S2 on the 1, 0, so what we're doing is we are, since the 1, 0 was, if you remember up here, the up down plus the down up. So we have to add both of these results together. So we have to add this one to this one here. And so we do that right here. So we have the S1 times S2 acting on this. We have our 1 over square root of 2 here. We're acting on these. So once again, this is the next step. There's just a lot going on here. This is just sort of distributing each of the components to each of these. Then we actually do the flipping of the arrows and putting in the eigenvalues. Then we sort of put everything back together. So we multiply all these eigenvalues where there's multiplication and put the arrows back together into the same ket. Then we end up here. We kind of keep going down and we end up with this. But we see that this part here, this 1 over square root of 2 times this these degenerate states here is just equal to the 1, 0. And so it's just this times our, times our 1, 0 state. And so we can do the same thing for the 0, 0. We end up with this, which is just equal to our 0, 0. And so we end up with a minus 3h bar squared over 4 times r 0, 0. And so we know that the s square things from a previous video, when we act that on our state here, we just end up with 3h bar squared over 4. And so we can fill in the rest. So we have our first s squared and our second s squared. So that's where this and this come from here. We have our s1 times s2, which is where our h bar squared over 4 comes from. It was this one. And then this 2 because we have to multiply by 2. And so when you end up adding all these things together, so you end up with a 6 over 4 plus 2 over 4, which ends up being 8 over 4, which is 2, so 2h bar times this, which means the eigenvalue is this. And so if we do that with the 0, 0, so instead of using this, which I have in the lighter blue up here, we use this one in the darker blue here, but we just do the same calculations and we end up with a 0. So the eigenvalue for the 0, 0 state is 0. And then this is where it starts getting into what Griffith uses or leaves for the reader as homework. So once again, we're looking at just the S1 times S2 part acting on 1, 1. So we end up with this after doing the calculations. So then when we act the entire thing on our 1, 1, so we add these together, we end up with our 6 over 4 plus 2 over 4, which is 8 over 4h bar on 1, 1. So once again, we end up with 2h bar times our 1, 1 state. So that is our eigenvalue. We do the same thing again for the 1 minus 1. We end up with this. So we then use the entire thing here. We have our 3/4 h bar squared plus our 3/4 h bar squared plus the h bar squared here, or the 2 over 4 h bar squared. And so once again, we end up with our 2h bar squared as our eigenvalue. And so what this tells us after everything is said and done, so when we act the s squared on the 1, 1, or on the 1, 0, or on the 1 minus 1, we get the 2h bar squared as our eigenvalue. And so the 1, 1 is when our m1 plus m2 is 1/2 plus 1/2. This is when it's 1/2 plus minus 1/2, or minus 1/2 plus 1/2, and this is when it's minus 1/2 plus minus 1/2. And so that's where the 1, the 0, and the minus 1 come from. And then so when s equals 0, the eigenvalues of our s squared is 0. And so that's when the m1 plus m2 is equal to 1/2 plus minus 1/2. And I guess it could also be minus 1/2 plus 1/2. And so once again, this is just looking at this. Up here is our triplet state right here. This is our singlet state. So the triplet state is when we can have both of them pointing up, both down, or we can have one up, one down, or one down, one up from there. So the spin of two particles will range from S1 plus S2 to S1 minus S2 the following way. So it goes from S1 plus S2 to S1 plus S2 minus 1 to S1 plus S2 minus 2, and so on and so forth until you going down by an integer each time until you get to S1 minus S2. So for instance, S1 equals half, S2 equals half. It goes from 1/2 plus 1/2 to 1 to in 1/2 to minus 1/2 to 0. So that's our spin. Or if we wanted to look at kind of another example, if we have the spins S1 equals 2 and S2 equals 3/2, then we just do these calculations and we go from a total spin of 7/2 down to 5/2 down to 3/2 down to 1/2. So that is how the total spin of the two particle system works. So now we get to the Clebsch-Gordan coefficients. I think once again I've only ever seen this written, so if I'm mispronouncing it, I guess you can feel free to let me know. So Clebsch-Gordan. So this is kind of the I guess general form of it. And so these C numbers right here are the Clebsch-Gordan. And so if we want to make this more explicit, so we see that we have our C, and we keep the S1, S2, S on top. And then we go from M1 and minus M2, where M stays constant for our system. And then in the next one is the M1 minus 1 and M minus M2 plus 1. And then we can keep going until we get to minus M1 and M2. So, this could be multiple things, but we can use this example here. So if we have S1 equals 2 and S2 equals 1, then our M1 will range from 1 to 0 to minus 1, and our M2 from minus 1 to 0 to 1, meaning that our M1 plus M2 stays equal to 0. And so I put up here, these are the S's. So the first one is the S1, which is 2. The second number is the S2, which is 1, and then the third number is S, which is just S1 plus S2. Then we see down here, we have the first one here is our M1, then this is our M2, and then M1 plus M2 is this third number here, this 0. And we keep going with this, so the top stays the same because we still have the same amount of spin, but now we're at the 0 and the 0, and M1 plus M2 is still equals 0, and then we get to the minus 1. We get to the minus 1 for M1, the 1 for M2, and then the 0. And you can see in the kets here as well that I go from 1 to 0 to minus 1 here, then minus 1 to 0 to 1 here. And then, so the next thing to think about is, how do you actually get the number C? What number do you actually use for it? And you can kind of see the spoiler here, but it comes from this big confusing looking chart. And so I've just cut out this part that I have boxed in red here. And so what you see is, so our total spin is equal to 3. So that's the 3 up here. That's the S. That's what this top number on here means. And then our total Z component is equal to 0. That's our M1 plus M2 equals 0. And then we can go down to here, and we go from the M1 is plus 1 to the and M2 is minus 1. So we end up with this 1/5. And we put 1 over the square root of 5 here because of the Born rule. Then for the 0, 0, which was this second number here, we take the 3/5, put it under the square root there. Then for the -1 to 1, we do another 1 over square root of 5 here. And so that is actually what we substitute in for those c's on there. And so, yeah, here I just said we use the square roots because the probability is the square of the coefficients, the Born rule. And so it should add up to 1. So, 1 over square root of 5th squared plus square root of 3/5 squared plus 1 over square root of 5 squared equals 1/5 plus 3/5 plus 1/5 equals 5/5 equals 1, which is what we would want because that is our probability of 1. So it should add up to 1. And so, yeah, I think that was everything I wanted to talk about in this video. So yeah, this was the addition of angular momenta. Like I said, there's, conceptually it's fairly easy. It's just a lot of this calculation and tedious bookkeeping and stuff like that. But once again, I'll leave a link to this very sheet, these lecture notes in the description down below if you wanted to sort of go through it by yourself at a slower pace. But I hope this helped you understand this a little bit better, and I will see you in the next video.